Good evening, everybody, and thank you very much for joining us for tonight's Kibi Science Lecture, either right here or somewhere online. My name is Thomas Baumgart. I'm a professor in the Department of Physics and Astronomy here, and I also recognize that I can take my mask off now. What I was trying to say is that I'm in the Department of Physics and Astronomy, and it's really my great pleasure to introduce our speaker tonight, Professor Aomawa Shields from the University of California, Irvine. Before I do that, though, let me tell you a little bit about the Kibi Science Lecture. Dr. Frank Kibi was born in 1915 and graduated from Bowdoin in 1937. After completing medical school and serving in World War II, he returned to Maine and became a pediatrician in Lincolnville. And I understand that he was actually known to hundreds of families throughout the Mid-Coast region as the baby doctor. Among Dr. Kibi's many interests were music, science, and research. In fact, he himself studied embryo implantation in farm animals, which led him and his wife, Lucy, to live in New Zealand for about a decade. Throughout his life, he also supported young people in ways that extended well beyond attending just to their medical needs. For example, he was instrumental in the founding of the Bay Chamber Music Series. He became a supportive friend to many aspiring musicians, and he also endowed not one, but 2 science fellowships here at Bowdoin. And then, in 1994, he established the Kibi Science Lecture Series in astronomy and geology. This lecture series has allowed us to bring numerous prominent and renowned scientists to campus and engage with the Bowdoin community, discussing topics such diverse as cosmology, earthquake predictions, gravitational waves, merging black holes, and the effects of climate change on urban coastal areas. This particular Kibi Science Lecture has been in the planning actually for a long time, and I would like to take this moment to thank Christine Sullivan in the Office of Steward Programs, and also my colleague, Madeline Saul, for all the help and work along the way. I first reached out to Professor Shields in 2019, eager not only to have her tell us about her groundbreaking research into the habitability of distant stars, distant planets orbiting stars, but also about her extraordinary efforts to open the doors of astronomy to people who have long been underrepresented in our field. Now, if you need a hint as to why this has been in the making for so long, let me know, okay? And frankly, we've been hoping for an on-campus visit for a long time, but finally we decided that we did not want to wait to hear any longer, or that we did not want to wait any longer to hear from Dr. Shields, and that's why I'm thrilled that she can join us tonight, at least virtually. Dr. Shields has been a professor of physics and astronomy at the University of California, Irvine since 2016. She received her undergraduate degree in Earth, Atmospheric, and Planetary Sciences from MIT, and her PhD in astronomy and astrobiology from the University of Washington, embarking on a line of fascinating research into distant worlds. Essentially, she uses computer models, including those that are traditionally used to predict weather patterns here on the Earth, along with data from ground and space-based observatories to determine whether planets orbiting faraway stars may have the kind of atmospheres and may meet other conditions that might make them habitable. Her research has been recognized with many awards, including an NSF Career Award, a Clare Luce Professorship, as well as Kavli and TED Fellowships. Now, all of this alone would make her CV really quite impressive. But there's another, somewhat surprising side of Dr. Shields' background. She is a classically trained actor who worked professionally on the stage and screen for several years, even earning a Master's of Fine Arts from UCLA. Moreover, she has blended her passions for scientific exploration, for the creative arts, and for creating opportunities for groups underrepresented in astronomy by establishing an organization called Rising Star Girls. Rising Star Girls works with girls at an impressionable age in middle school and explores astronomy with them in non-traditional ways through writing, theater, and visual arts. It encourages and inspires those girls to consider the big questions that astronomy poses and perhaps even think about a career in astronomy or other fields of science. And I hope you tell all of them about Bowdoin, by the way. Okay. Another topic that is often on Dr. Shields' mind is the work-life balance. In fact, we might summarize all her efforts as the search for habitable environments on Earth and elsewhere. She will reflect on many aspects of this search and her unusual and fascinating path through the arts and sciences in her upcoming memoir, which is scheduled to appear in 2023 and which I'm looking forward to reading. In the meantime, though, I'm very excited to hear about what she has to tell us tonight. And I would therefore like to ask you to please help me welcome Professor Shields through the magic of technology to Bowdoin.
Thank you so much, Tomas. Thank you, everyone. I'm thrilled to be here tonight and to have been invited to be your Kibbe Science lecturer this year. I regret that I can't be there with you in person, but I hope by the end of this event tonight, it will feel almost as if I have been there with you. So I'm going to share my screen. And here we are. So before I get to anything else in this talk, what I want to do is cover what I consider to be the most important part of any event that I facilitate, and that is how to pronounce my name. Tomas had it perfectly, and what I like to do is to have some sort of interactive part of the program, and this is it. This is one of the interactive parts of the program, the first one. So my name is pronounced, as Tomas did excellently, Aomawa. There are a couple ways you can do it. The sort of entry-level way is to sort of have a glottal stop between the A and the O so that it sounds like Aomawa. And if you feel comfortable doing that, then you can move on to the next level pronunciation, which is the preferred pronunciation, which is no glottal stop, which means you don't stop the flow of air in the back of your throat between the ah and the o. So it sounds more fluid like this, Aomawa. So I'm going to count to 3 and let's all say my name together. 1, 2, 3, Aomawa. And I wish I could hear you all. It's usually a lot more fun when I can hear the cacophony, but I trust that it really is music to my ears, and thank you. I'm also going to do something else a little bit more non-traditional, which is invite you to participate with me in a few moments of secular mindfulness-based meditation practice. So over the past 2 years, the lines between personal and professional have blurred, as we know, due to our external circumstances. And ever since I started at UCI, I have integrated some sort of mindfulness practice into my courses, into my research and education group meetings. And so I'd like to do that now more on the presentations that I give. So those who would like to, of course, completely optional. If you'd like to, I invite you to close your eyes and sit back in your seat. And notice where your body is making contact with the floor, the chair, whatever surfaces are there. And what is the nature of that contact? Is the surface cool, warm, rough, or smooth? What other sensations are you noticing in your body? Are there muscles that feel tight or relaxed? And what is the quality of your breathing before you adjust it in any way? Does it feel deep or shallow? Where do you notice the breath most strongly? The lower belly, the chest, the throat, perhaps that space right below the nostrils above the upper lip. Wherever you feel your own breath most strongly, focus there for a moment. And let's take a couple of deep breaths in through the nose and sigh it out through the mouth. And again, in through the nose and out through the mouth. And then return to your natural breathing. The most natural process, the most acute signal that we are all alive. In many ways, it can be so easy to forget that we do it. That all day long we're breathing in and out. And yet how miraculous to be alive on this earth at this time, this single moment in time in the Earth's 4.5 billion year history. We get to be alive now. It's our turn to be alive now. Within the universe's nearly 14 billion year age, we're alive right now. How precious. And I'm going to float a question to you. And that question is, that I'd like you to ask yourself is, what do I need? What do I need? There is no wrong way to answer this question. Whatever that looks like for you, however you receive that question, allow it to settle in your body as you breathe. And see if anything comes up. See if there's anything there at the bottom of your awareness that wants to rise up. And then whatever has arisen, acknowledge it and let it go. Trusting that it will be addressed at the appropriate time with your full attention. You don't need to do any of that now. All we need to do is breathe. Let's take one more deep breath in, perhaps the deepest breath we've taken all day. In through the nose and sigh it out through the mouth. And gently wiggle your fingers and toes. And when you're ready, you can open your eyes. Thank you to those who participated with me. I'm also going to show you something that you may not typically see in science lectures. And that's a picture of my family. I think it's important to sort of tear down those walls between what we think a scientist or a professional is and does and what they actually do, their life. And so it's important for me to show you, especially those of you who are students who might have any sort of preconceptions about what you need to be or have to be to get into this field. You get to have a full life. I have a full life. I have a husband and a 4-year-old daughter, and I have lots of hobbies and things I like to do outside of the office. And I'm here to tell you that it's possible to have a very fulfilling, full career and work 40 hours a week or less. I am living proof. You don't have to be out of balance to have a great job and a great life. And that's something that I will continue to be an example of as the years go by, and I hope to be able to assuage any students' fears in that regard, that you get to be who you are and do the thing that you love. Our planet orbits one single middle-aged star in a galaxy of hundreds of billions of stars, in a universe of hundreds of billions of galaxies. This is one of my favorite images of our universe. It's called the Hubble Ultra Deep Field. And it was taken, so those of you who are photographers or photography buffs know that when you stare at something and you open the shutter, you need to open the shutter long enough to get the appropriate amount of light in from the source. And in this case, Hubble, the Hubble Space Telescope, was staring at one patch of sky, and it was looking back in time, looking at these distant galaxies. And so it had to keep that shutter open for multiple days to get the light that we're seeing here in this image. Hundreds of hours. And what's great about this image is that just about every point of light you're seeing here is not just an individual star. It's an entire galaxy full of hundreds of billions of stars. So we're living in a whole new universe now, where once it was believed that the planets within our own solar system were the only planets existing in the universe, we now know of close to 5,000 planets orbiting stars other than the sun, which we call extrasolar planets, or exoplanets for short. And this nearly 5,000 exoplanets spans a number of different regimes. There are planets that are ice giants, similar to Neptune and Uranus. There are planets that are gas giants like Jupiter. There are planets that are considered super Earths, which means they're between 1 and 10 times the mass of the Earth. And there are planets that are on the order of Earth's size. Of course, this is my other favorite image of the universe, and it's of our own planet. And it was taken by the Apollo 17 mission, which was the last human mission to the moon in 1972. And of course, this planet is the only planet that we absolutely know unequivocally hosts life. But now, thanks to several missions, we have on the order of a dozen or a couple of dozen, depending on who you ask, planets that could be in the regime or in the region of space from their star where they might be able to host liquid water and therefore life. And we know about these nearly 5,000 planets now, exoplanets, largely due to NASA's Kepler mission, which is another space-based mission that operated for nearly 10 years. And this mission looked at one particular patch of the sky towards the constellation Cygnus. And all it did for nearly 10 years was look for dips in the brightness of stars in this region caused by planets passing in front of those stars. This technique is called the transit technique. And this is exactly what Kepler did. It peered at these star after star, over 150,000 of them, and watched for dips in the brightness of those stars due to the planets passing in front of them, and allowing us to measure things like the size of those planets, first to detect that the planet was even there, and then giving us information about the planet's size. We now have a successor to Kepler, the Transiting Exoplanet Survey Satellite, or TESS. And TESS, unlike Kepler, which stared at one tiny patch of the sky and looked for these dips in brightness, TESS is an all-sky survey. So just for that reason alone, we're going to be discovering even more planets in the coming decade. Plus, TESS is looking at stars that are much closer to us than Kepler's 150,000 stars. TESS's stars are going to be considered in the solar neighborhood. So these stars, we're looking at their brightness. When we see dips, we check and check. Then we can confirm that those are planets doing the dipping. And because these planets are orbiting stars in the nearby solar neighborhood, that means these planets are going to be easier to follow up on with the next generation of space-based missions, like the James Webb Space Telescope, which just launched around Christmas time. Super exciting. It's going to be doing a lot, revolutionizing our view of the universe across a number of different astronomical phenomena. But one aspect of that focus for JWST is looking at planetary atmospheres. And it's not just space-based missions that are going to be doing the observing. It's a concerted, combined effort between space-based missions and ground-based, what we call extremely large telescopes, or ELTs. Many of them are coming online or already are online. And so together, we're going to be getting the best, most up-to-date information about these really scientifically interesting planetary targets for habitable planets. Some of the planets we've already discovered, wanted to give some highlights, include the TRAPPIST-1 system, which hosts 7 planets orbiting the very cool star TRAPPIST-1. And about 3 of these planets are considered possible, potentially habitable. They're in a certain region of space, which we'll talk about shortly, where they could host surface liquid water and habitable conditions. But they're all Earth-sized, as you can see. Another planet that's exciting is Proxima Centauri b, particularly compelling because it orbits the closest star system to us, Proxima Centauri. And again, even though it's just over 4 light years, which a light year is the distance light travels in a year, so that's on the order of 10 trillion kilometers. However, that's virtually down the block when we talk about astronomical distances. And having a planet that close that's in its host star's habitable zone, which again, we'll talk about shortly, means that we could have a potentially habitable planet in our relative backyard. The planet LHS 1140b is also interesting for different reasons. We can get radius information from that transit technique that Kepler and TESS are both using. For this planet, we have that radius information. And for this planet, we also have mass information from another technique that we use called the Doppler or radial velocity technique, which measures changes in a star's velocity due to a planet pulling on it. So we have both mass and radius information. And those of you might remember from your geometry classes that when we have mass and radius information, so information about mass and size, that allows us to constrain an important property about planets, and that's the density. And this information tells us that LHS 1140b, while not having the most romantic name, is likely to be rocky. And that's exciting because if a planet is rocky, meaning we could stand on it, then it's likely that oceans could sit on it. So this is really great when we can get planets' mass and radius information for these planets, because it allows us to get and constrain and quantify even more information about these planets, leading to the conclusion that they could be like the Earth. And TESS, in its few-year history already, has started to find planets in the Earth-sized regime. And here's a few of them showing you to scale with the Earth. So there's no question, we are discovering other Earths in terms of size. The remaining question, of course, is, are they other Earths in terms of their atmosphere or their potential to host life? One of the most revolutionary aspects of this field has been that the realization that our solar system is not the standard model, but rather one of many possible configurations that are out there. And we're going to keep discovering tens, hundreds, perhaps even thousands of planets over the next decade or two. And that leads us to what I consider to be a quality problem, if you will, which is that we're not going to have infinite telescope time to follow up on every single one of these potentially habitable worlds to determine if there's really life there. We're going to need to prioritize those planets to follow up on. So how do we do that? Before I tell you that, I want to take a step back and tell you how I got to the point where I'm able to address this question using the techniques that I use and that my team uses. So many of you remember that old essay in school, that what did I do for my summer vacation? So I'm going to entitle this video essay, How I Became an Astronomer and Astrobiologist, but my hope is that it's going to be much more enjoyable. So this is my grandmother. She majored in mathematics at Tennessee State University in the 1930s. As rare as African-American women are in STEM fields today, in the 1930s in the South, they were virtually non-existent. My grandmother raised chickens to put herself through school. One day the chickens escaped, and that was the end of her college career. Before that, she sat in the front of the lecture hall. She was rarely called on, mostly ignored, but she never gave up. And I remember always seeing this stack of accounting textbooks on her bedside table. She ended up becoming a civil servant at Miramar Air Force Base in San Diego, home of the Blue Angels aerial flight team. And she was always learning and passed that love of mathematics on to me. I dedicated my PhD dissertation to her. This is my mom and me at her master's degree ceremony. So I am not the first in my family to get a doctorate. That distinction belongs to my mother. She went on to become a professor of music theory and composition. And here at her master's ceremony, we were both beaming with pride. What I learned from both she and my grandmother was that education was a vehicle to a better life and to more options. This is my dad. He is a professional musician like my mother and has his own performing arts company, tours the world. He and my mother were in a band called the Pyramids, and they toured the world playing music, and the band got back together again recently and have been touring and cutting more albums. My father is an incredible business person and boasts never having had a day job, which I particularly admired. As an artist, that's a tough distinction. So I got an incredible work ethic from my father. So here's one of the album covers of my parents' band. Can you see them? If we were here, if I was there in person, I'd be able to see what you're pointing to or who you think they are, but I'm gonna have to tell you, and you're probably right. There they are, right there, in their 1970s vest. Okay, so here are the facts. My parents are musicians. My grandmother liked math, studied it for a while. I learned that school was important. Wasn't like I came from a family of scientists. No one ever told me, you should be a scientist. But what I took from this was it didn't really matter, that all that mattered was how much I loved something and how hard I was willing to work to get good at it. When I was 12, my 7th grade class was shown the movie Space Camp, about a group of kids that get accidentally launched into space on the space shuttle. And this rocked my world. I ran home after school. I went to my trusty set of World Book encyclopedias. I pulled out the volume labeled A and I looked up astronaut and astronomy and spent the whole day reading about those two subjects. And World Book encyclopedias are really great because they have glossy pictures, and I plotted my entire career trajectory that day. I was going to get a PhD in astronomy from MIT, the best science school in the world. And after a couple of years of progressive experience, I would apply to NASA and to the astronaut candidate program. And I stuck pretty close to that trajectory. This is actually me at the prep school I went to, Phillips Exeter Academy in New Hampshire. But even then, I had my dream, and so I had my sweatshirt and I was ready. I'm not sure what I'm doing here with my feet, but enjoying dreaming about MIT. And I, as I said, stayed pretty clearly on that trajectory through college. But something happened along the way, and that was that I started to do acting at Exeter and at MIT. And I found that I loved that. I loved telling stories. But I did end up going right into graduate school after MIT. I went right into a PhD program in astrophysics at the University of Wisconsin-Madison. But I didn't make a real conscious choice there. I went right into that program because I thought that's what you do. You go right into PhD. So in a way, I was sort of on autopilot, and I had my head, one part of my brain was on the problem sets. The other part of my brain was dreaming of movies and the Oscars and what was the next film coming out. And I was distracted, right? It was hard to focus. And as I started to do poorly, I isolated. And I always loved those movies and TV shows that had a sci-fi focus. And it didn't have to even be space. It could be the ocean, but something about that quest for discovery and journeying into the unknown that I found really compelling. And I was at a crossroads. I wasn't sure whether I wanted to do the things the actors themselves were doing, or if I wanted to do the things the characters the actors were portraying were doing. I looked around me, myself and my PhD program, and I didn't really see many people who looked like me. They all sort of looked like this. And I took that to mean that I shouldn't be there. Right? That was another mistake. So I left. I auditioned for acting schools and got in to UCLA and moved out to Los Angeles. And I did some incredible things in Los Angeles. I acted in a film called 9 Lives that went to Sundance and was one of Ebert and Roper's top 10 films of 2005. I hosted a science TV show called Wired Science, which was my first indication that maybe these two loves that I had, acting and astronomy, didn't have to be so disparate. that they might, and there might exist some dimension in which they could coexist. I also did a lot of theater. This is me acting in Greek, I think it's Andromache in The Trojan Women by Euripides. And this scene, I'm saying goodbye to my son who's about to be flung off the cliff, because that's what happens in Greek tragedy. But, you know, I kept thinking about the stars. I would be driving through rush hour traffic to get to some casting room with terrible fluorescent lighting to audition for something. And then my eyes would go up, and through the smog, I would see a couple stars. And that kept happening. And I remember a point when my husband and I were in Florence, Italy, where we traveled for New Year's back in 2008, I believe. And I was standing in front of Galileo's tomb at Santa Croce Church. And I became willing to return to grad school, to fill out the applications, to study for the dreaded physics GRE, and to go back if that was what I was meant to do. And so we got back to the States, and I started doing that process. And at the same time, I took a sort of day job working in support of the Spitzer Space Telescope at Caltech, which is another space-based mission besides Hubble. This space-based mission is looking at the universe with different lenses on. Instead of visible eyes, Spitzer had infrared eyes. So it was really good at looking at dust and young star formation. And while I was there at Caltech, I started to go to astronomy talks. And I found that the ones that had to do with exoplanets were the ones that kept stopping me, that made me want to learn more about them. And this field that had really exploded during the 11 years that I had been gone from the field. So the first planet discovered around another star like the sun was discovered in 1995, around the time when I finished at MIT. And then here we were at about 2008, 2009, and we had discovered many, many more planets. And this field was really getting traction. And I realized that I wanted to be a part of those discoveries. So again, went to Italy, really surrendered to the whole process of whatever I was supposed to do, and got into grad school again and decided to change my life in Hollywood, to exchange it for a life in the Pacific Northwest at the University of Washington. So what I did right at UW, the second time around in a PhD program in astronomy, was I didn't isolate. In fact, I did the complete opposite. If there was a program that had my name on it, I was there. There was a program for for women who were coming back to school after a significant time away. I signed up. There was a graduate process group for women of color and the mental health center. I went. There were, when it came time to study for our qualifying exam, which is this dreaded exam it covers 13 courses over 2 years, and it's a 6-hour exam, and it's super, super hard. I showed up to study with my friends. I did not try to do that on my own. I drilled problem after problem, because in physics and astrophysics, there are only so many types of problems that you can be asked. And this is for the students who might be taking physics courses right now and struggling. It's all about drilling problems. There's only so many 3-body force diagram problems that you can be asked. There's only so many spring constant and pendulum problems. There's only so many ways that you can be asked how to use the kinematic equations. And once you learn the number of the ways to do those problems and do them over and over again, they become second nature to you. But often the mistake people make, and the mistake I made the first time around, was not doing enough problems. And really, I didn't make that mistake this time in grad school. It was like learning so much of it for the first time, but I was willing, and that willingness is so much of what matters. So I said yes to community rather than isolating and thinking that I was alone and was supposed to be. And I said yes to a life outside of academia. When I came back to grad school, I was 34 years old. I was married. I wanted to still be married by the time I finished grad school. So I needed to show up for that. However, I also had a very understanding husband who got that for the next 5 years, my primary focus was going to have to be studying and doing research so that I could actually get what I was there to get, which was the PhD. I was also quite laser focused. I didn't have that, should I be in this field as much. I also didn't have that, what should I study? What do I want to do thing? It had taken a lot for both my husband and I to move to Seattle. We'd given up really well-paying jobs. And so I knew what I was there to do, and I wasn't there to mess around. And so I devoted myself to that, the exoplanets as my research focus, and astrobiology, which was this newer field compared to astronomy, much newer compared to astronomy. And it's the study of how life got started on the Earth, how it's evolving, and how widely distributed it might be elsewhere in the universe. So this is a picture of me at my PhD pudding ceremony. So for those of you undergrads who plan to go into grad school, eventually you'll get to that point where you go to a ceremony and they put the hood, which is this part right here, they put that over you. Usually your advisor shows up and does that in a very ceremonial way. And that sort of signifies you leaving the student life and crossing over into the realm of the professoriate. This is my husband. He was running about 103 fever that day, but this was, of course, the time pre-COVID. So showing up with a fever wasn't that big of a deal. and he was not going to miss that day for anything. So that's him helping me with my hood. This is my dad. I swear to you, we did not coordinate. He is really that fashionable. So while I was in graduate school, I attended a journal club talk, and a senior grad student was sharing about a paper that he'd read about water, ice, and snow, and how the feedback that we typically associate with ice and snow, and an ice albedo feedback, would be different on planets orbiting a different kind of star from the sun, and how that could influence the climate of those planets. And as a grad student, you're always wanting that moment, that light bulb moment when you're like, this is what I want to study, because you're going to be doing that thing for 5 or 6 years, and it darn well better be something that you actually enjoy, that makes you want to get up in the morning every day and work on it. And this was the moment for me. This was that moment when I said, bingo, that's what I want to work on. And I wrote to the first author and asked if he was going to do any more work in that area. He said he wasn't planning to, that I could take it and run if I wanted to, but he asked if that he'd be co-author on any future papers. And I ended up we wrote 2 papers on this phenomenon, because this paper was a suppositional paper. There hadn't really been much else done with models or anything. And so this property of ice albedo feedback, that we typically think of ice as being a very bright white thing on our planet. And the more light that ice reflects, the colder the planet gets. Reflects more light back to space, temperatures get colder, etc. It's a positive feedback process. But ice albedo is different depending on the type of light it's getting. And that sort of property, starlight interacting with the planet's surface, really influenced my career. I wanted to devote most of it to looking at this interaction between the type of star and its light and the kind of surface that could exist on a planet. Because ice absorbs longer, redder wavelength light and reflects shorter, bluer light. Okay, I'm going to say that again. Ice absorbs longer, redder wavelength light, reflects shorter, bluer light. That's why this iceberg is so blue. So when sunlight hits the ice, the redder part of that light, so redder part of the visible and infrared light, gets absorbed on the way through the ice. And it's only the blue light that makes it all the way to the bottom. And then it gets reflected back up to our eyes and we see blue ice. And you can see this contrast very strikingly in this photo. So this blue marine ice, you see that blue so clearly because there's not a lot of cracks in the ice. So that property of the sunlight being able to make it all the way to the bottom, the blue light making it all the way to the bottom and get reflected back up, we see so much blue. Whereas the finest grained ice, which is snow, such fine grains, so many scattering opportunities, we don't see that blue property. So the way that we explored how this phenomenon of how ice albedo feedback could be different depending on the type of light that comes in from the star, we used global climate models, three-dimensional global climate models. And these models have been used for many years to predict climate change into the 2100s. So we see here the global warming in degrees Celsius as a function of the year, and this trend with global warming going up and up and up, that is all us. That's anthropogenic, which is a fancy word for human-made. So that's what we're doing to our planet's climate. And GCMs have been instrumental in highlighting this unfortunate fact. But there are a growing number of us who are using these GCMs, so global climate models, I'm calling them GCMs for short, to look at the climate and weather patterns on exoplanets. There isn't just one type of surface that could exist on an exoplanet. There's many surfaces beyond ocean. We could have ice, we could have salty ice, which is what can happen when a liquid water fills a brine pocket and then that liquid crystallizes into something called hydrohalite, which blocks the light. That has its own albedo feedback. Land could be on a planet, and the way that the star's light interacts with that surface will be different depending on how the light from the star is distributed across the electromagnetic spectrum and what the surface itself is doing, how reflective that surface is at different wavelengths. So in short, the surface matters to climate and habitability studies. So this is certainly one way that we could look for life on other planets by listening. And there are people that are doing that, people especially at the Search for Extraterrestrial Intelligence, SETI, which is still active. It was popularized in the film Contact based on the book by Carl Sagan and Ann Druyan. This is another way. This is the way that I look for life elsewhere, using observational data that we have, and when we have it for these scientifically interesting planets that are discovered, and theoretical computer models. And it's this two-pronged approach that we need to be able to prioritize the planets that we want to follow up on with next generation space-based and ground-based instrumentation. All in service to the goal of finding what I consider the holy grail in the field of exoplanet research, and that's the discovery of another habitable planet like the Earth that is capable of supporting and maintaining life at the present time, maybe even hosting it right now. So when we think about what life needs to survive on the Earth, there are three major requirements: a liquid, which on our planet is water, a suitable environment for the formation of organic compounds from bioessential elements, sulfur, phosphorus, oxygen, nitrogen, carbon, hydrogen, okay, we say SPONCH for short, and some sort of energy source, whether it's from the star or from chemistry, from potentially water interacting with rocks, for example. Now, a terrestrial planet by nature has some sort of energy source along with the basic building blocks in some form that are needed for life. But what isn't as common is liquid water. And that's because it requires a specific set of temperatures and pressures that are needed to keep water in liquid form. Life on Earth uses a diversity of metabolisms, but they all require liquid water for chemical bonding and as a solvent for chemical reactions. And so it's liquid water that drives our search for life elsewhere. Of course, it's not the only way that life could potentially exist, but it certainly is on our planet. And so we use that as our model. So this habitable zone that I mentioned uses liquid water as its main criterion. So the habitable zone is the region around a star where a planet with an Earth-like atmosphere could keep water liquid on its surface, could be warm enough. Too close into the star and the oceans are in danger of boiling away to space in a runaway greenhouse state. And too far away, the oceans could freeze. But unfortunately, it's not this simple. It's not only about orbital distance. If it were, then it would be very easy for us to determine where life is. We just find a planet that orbits its star at this distance and we'd be done. But it's much trickier. And there's many different factors that can affect the long-term presence of liquid water. So if we think about that, what governs a planet's ability to sustain liquid water on its surface over long timescales? There are a lot of things. So there's the effects of the star, there's the planetary systems, unique orientation and structure, there are the planet's properties, how the light from the star is distributed with wavelength, stellar activity, the evolution of the orbits of the planets, whether there are other planets in the system. I mean, it just goes on and on. And so what I'm showing you this diagram for is really to overwhelm you, because sometimes I get overwhelmed when I look at this diagram. However, our team has been slowly chipping away at many of these factors, trying to figure out what's most important. What are the governing factors that really influence a planet's ability to be habitable on its surface? And we've had a particular focus over the last 5 years or so, and it's a specific class of planets orbiting these small, cool, red, what we call M-dwarf stars. So a little primer on stars. This is the sun. We're a G star or a G dwarf star. And those M stars are over here. They're also called red dwarfs. So they're much cooler and smaller than the sun. You can think of M dwarfs as like the tortoises of the stellar family. They burn through their fuel really slowly, and therefore they live for a long time, hundreds of billions, and in some cases, trillions of years. No M stars have ever died. Their lifetimes are longer than the current age of the universe. And juxtapose that with the hottest, most massive O stars, which are like the James Dean of the stellar family, right? They live fast, they die young, they burn through their fuel like that, and in a few million years, they're gone. Right? That's not very good, given that we think that it took life on the order of 500 million to 1 billion years to get a foothold on our planet. This is one of the reasons why we're particularly excited about the prospects of life on planets orbiting M dwarfs, because those stars would offer long time scales for planetary and biological evolution in the system. M stars are also the most numerous type of star in the galaxy. So this diagram that shows all known stars within 10 parsecs or 33 light years of the sun. So these are all the different classes of stars. You can see here at the bottom, the M's, they comprise 70% of all stars. So 70% of stars, when you look out at the sky at night, 70% of those are these small, cool M stars. So they offer the best chance of finding habitable planets through sheer numbers alone. It's also easier to detect planets around these small M stars. So a lot of advantages, and a newer one that we discovered, or that I discovered as part of my dissertation work, is this ice albedo effect. So if we put ice on a planet orbiting a star like the sun, most of that light would be reflected because ice reflects strongly where the sun emits strongly in the visible part of the spectrum. So I'm showing you here albedo, which is a fancy word for reflectivity, how reflective a surface is between 0 and 1. 1 being it reflects 100% of the light that it hits. 0 means it absorbs 100% as a function of different wavelengths. So this is the visible, and over here is the infrared. And we're seeing snow, blue marine ice, which you see here, an ocean spectrum, and then a land spectrum, and then some ice spectra in between blue marine ice and snow. Ice on a planet orbiting a star like an M star, a smaller, cooler, redder M star, would absorb most of the light that hits it, because ice absorbs strongly where the M's emit strongly, in the near infrared and the infrared. And so what we discovered is that planets orbiting M dwarf stars are harder to freeze over because that ice and snow is absorbing a lot of the light, so that those planets tend to be warmer than planets orbiting actually hotter, brighter stars at an equivalent distance where they get the same total amount of light from the star. These planets are harder to freeze, and if they were to freeze, they're easier to thaw out of these so-called ice-covered or snowball states. And that was an exciting result. We went on to look at land, because as I told you, there are many different types of surfaces other than ocean or frozen over ocean, right? A planet could have land. And so my postdoc, Andrew Rushby, looked at what happens if you increase the percentage of land on a planet and look at its global mean surface temperature. So, and that's what you're seeing here is the percentage of land and what the temperature would do for planets orbiting. Here's an Earth around the sun. Here's a planet around a hotter star than the sun. Here's a planet around a star a little bit cooler than the sun and a lot cooler than the sun, the M dwarf planet. What you see is the more land you have on this planet, the cooler the planets get. But still, the M planets are warmer than all the others. And that's because land can be pretty bright too. Remember I showed you, right? This representative land spectrum can be pretty bright, much brighter than an ocean-covered planet. And as that land percentage increases, so does the amount of starlight that gets reflected away. Right, so the take-home point there is that when the planet is dominated by land, it's reflecting more light away from itself, and then the temperatures go down compared to planets that are dominated by ocean. But we still have warmer land planets around M stars than around stars with more visible and UV light output. We also wanted to look at what would it happen if we actually applied this phenomenon to actual discovered systems. So we looked at the TRAPPIST-1 system and expanded our exploration of land surface compositions. So rather than that sort of representative type of spectrum I showed you before, we looked at different types of land surfaces: dune sand, granite, which is much more absorptive than dune sand, calcite, which is super reflective, something called iridisol, which is kind of like that clay spectrum I showed you before, the representative spectrum. And then there's snow and ice for comparison. And here's the spectrum of different types of stars. Here's the sun in yellow. There's that F dwarf star, which is a little bit hotter than the sun, so it's skewed a little bit more towards the visible part. There's a K that has a little bit more infrared than the sun, and then there's the M. This is TRAPPIST-1, a very, very ultra cool M star that has a lot of its light output in the near infrared. What we found was that when we changed the surface, the land surface composition, we could get a difference of about 50 degrees in global mean surface temperature between the most absorptive and the most reflective land surface composition. And it wasn't just about the albedo effect of, more reflective surface reflects more light away. The land surface also affects what's going on in the atmosphere. So these are plots of equatorial energy transport. So how energy is transported across the equator of the planet for a few of the different TRAPPIST planets, TRAPPIST-1 planets, D, E, and F. And also looking at the Earth as a comparison. And so here we're using the two end members of land surface composition, granite, the most absorptive, and calcite, the most reflective. What we see is that for the lowest albedo land surface, we have more energy transported across the equator. And when you have more energy transported, you're evening out your temperature contrasts and you're distributing more heat. And so we end up having a warmer planet, a warmer climate in those situations. As I said, you could have a situation where salt albedo feedback is relevant, where salt can precipitate through sea ice at low temperatures. And you could have a situation where a surface called hydrohalite, which is basically very, very salty ice, ends up being more reflective than snow in the infrared. This is, again, reflectivity or albedo as a function of wavelength. And what we find is that for the M stars, which, remember, emit a lot of their radiation, their light, at these longer wavelengths, having parameterizations for the formation of this surface type is critical in climate models, because when we do so, we see that these planets could be cooler than originally thought. If we don't have that parameterization, we don't get the accurate assessment of their potential climate. Recall that I mentioned that our solar system, which has all of our 8 planets orbit in roughly circular orbits, we're not the standard model within the exoplanet population. There are many planets that have highly elongated, what we call eccentric orbits, that take them in and out of the habitable zone. And what would these climates be like? Could these planets even host life over the course of their orbits? If they get so close to their sun, to their star, they could lose their oceans. Then they go really, really far away from their star where they could freeze. Is it even possible to have habitable surface conditions across an entire orbit? And my grad student, Igor Polupsky, looked at this and quantified the fractional habitability that we could see on a planet as a function of its eccentricity, or the shape of its orbit. And what we find is that, yes, planets orbiting these cool small M-dwarf stars, because of that ice albedo effect, end up being warmer and therefore thawed for larger fractions of their year when they have lower eccentricities, so a higher fraction of habitability when their orbits are on the circular side. But even for those highly elongated orbits, planets can still be habitable during a significant fraction of their year. Even when they're close enough to their stars to maybe undergo a runaway greenhouse, they never lose all their oceans. They still seem to retain some amount of water, which could still continue to support life. And then when they go to that farthest part of their orbit, they're not subject to full ocean freezing. So there's still some habitability possible, even in the most highly eccentric cases. With this habitable zone, though, it can be tricky, because as I showed you here, the habitable zone is quite close to M stars compared to hotter, brighter stars. And these closer orbits where it has to be to get the same amount of light, because these M stars are cooler than the hotter, brighter stars. In close-in orbits, you could have a situation where the planet has a perpetual day side. We call this situation synchronous rotation. Right, so if we look at the traditional habitable zone for our star, the sun, which is far enough away that we're able to maintain a fairly rapid orbit, the M star habitable zone is much closer in, right? Much closer to its star. So if we think about how our planet is able to have a really rapid orbit, 24 hours rotation, excuse me, it rotates 24 hours, and that orbit of 365 days around the sun. In a synchronous case, the planet's day is equal to its year. So it takes as long to rotate on its axis as it does to revolve once around the star. And there's been concerns raised about, right, the day side totally being searingly hot, the night side freezing out. You can imagine this atmospheric collapse, or at least, the very least, a snowball situation, versus becoming a runaway greenhouse and losing all of your oceans to space on the day side, right? So the night side having atmospheric collapse, the day side having the runaway greenhouse. What we've been looking at, my postdoc Anna Lobo has been looking at this possibility that life might only be able to exist along the terminator, which is the dividing line between the day and the night sides. And what would that look like? We call that scenario Terminator Habitability. And we've been able to show that under certain situations and with certain assumptions, it is possible to have a planet that's too hot on the day side, too cold on the night side, and only just right on the terminator. And so we're looking forward to sharing that work in the coming months. We call it, yes, Terminator Habitability. One of my grad students, Vidya Venkatazan, has been looking at sort of the real life case of a story that was popularized by science fiction writer Fritz Leiber in 1951. The story was called A Pail of Air, and it was about, in this scenario, Earth lost its star and became a rogue planet, and the atmosphere froze out in layers according to the gases in their phase diagram. And this family that thought they were the only ones alive on the planet lived in a deep, dark cave, and every day they got up and went out to the surface to fetch a pail of air to heat over the stove in the cave so that they could breathe. So it started to get us thinking, what would it be like if these planets were on these highly elongated orbits where they could freeze, the atmosphere could freeze out according to its content, right? Its specific gas phase diagram. Water ice freezes at 0 degrees Celsius, carbon dioxide ice next, methane ice, right? What would a climate evolution or climate stability look like when you juxtapose the farthest part of the orbit to then the planet being, sublimating back, that frozen atmosphere sublimating back into the sky at closest approach? Could that even happen? So she's been looking into that and getting some exciting results. Of course, the M dwarfs, because they live so long, they have really, really active early phases of their evolution where they spew out tons of X-ray and UV radiation towards the surface. And it might be that life would only have a chance of existing at the bottom of the ocean. But as we've seen on our planet, life finds a way. And there are many, many ways for life to exist. We've seen life on these arid regions, in Antarctica, the subglacial lakes, cave boreholes, steaming hot springs, hydrothermal vent environments. there's not a traditional way to find life. And so too, there's not a traditional way to live. I named this talk Searching for Life and a Life, right? And I wanted to do that because many of you who are students might be thinking that you have to be fit into an existing mold to pursue your dreams. And it might be that there are no role models for what you want to do. It might be that you have to be your own, but you're perfectly capable of doing that. And I also want to mention Rising Star Girls, which Tomas already talked about, which is this organization that I founded to encourage girls of all colors and backgrounds, particularly girls of color, so girls from backgrounds traditionally underrepresented in the sciences, to explore and discover the universe using theater, writing, and visual arts. Middle school is that age when girls start to get quiet. They start to raise their hands less often. They become more concerned with how they look and less concerned with how they think and feel about the world. And the creative arts are inherently personal. You can't tell someone who draws a picture that it's wrong. And we wanted these girls to look up in the sky and say, I wrote a poem about that star, or I painted a picture of that planet. And now we're talking about it actually hosting life. So that when the heavy math and science comes in, they will be less likely to abandon the field because they'll hopefully have that personal connection. Just as if we looked at the Milky Way in one type of light, we'd miss so much information. And if we looked at multiple wavelengths, so too is there so much more to these girls than meets the eye. So we have these projects where they get to make their own constellations and write constellation myths about them. They get to draw their own pictures, artists' impressions of remote sensing images, and artists' impressions of exoplanets that we know nothing about. They could be right for all we know. And we conducted our first virtual workshop. We've been doing in-person workshops for years, but this was our first virtual one last summer for almost 50 girls around the country. And it was a roaring success, and we look forward to this summer taking it globally. And we're seeing some great results in assessments where we ask them to rate their level of agreement on a series of science questions, like a science statements, like I see myself as a science person, or I talk to my family and friends about science. From before versus after the workshop, the results are quite encouraging. Especially the I see myself as a science person. So I hope that you'll visit the website and learn more about what we do and why we do it. So a few parting thoughts to the students in the room, or perhaps even others in the room who might be wanting some guidance. I've made use of a number of resources, both within academia and outside of academia, when it comes to charting my own career path and finding a balance between the different sides of myself. And what I've gleaned from all these different resources is that it's important to put as much time as we put to learning a subject or doing an assignment, put that time into learning about ourselves, and even more time into loving what we discover. I took part in a program after tenure where I got to sort of make a conscious choice about what I wanted my post-tenure career path to be before that path got determined for me. And what I discovered was that what I love doing is using my experience to inspire others to embrace their whole selves and their full potential. Who I am is a champion of interdisciplinarity. And these are my core values: kindness and healthy personal, family, work-life balance. And what I wanted to do for the next 5 years post-tenure is share my story as broadly as possible through writing and speaking. And so thank you for being part of this vision manifested. What would it be like if you did something like this for your own life? Discover what you love, who you are, being able to put words to it, interview people who are doing what you think you might want to do, which will help you determine what's not for you and what might be for you, and make a choice and see where it goes. Develop your own values, and this is the hard part sometimes, trust them. Have a life, as you've seen before, like that's really important to me, right? Have a life, have interests outside of your career, because the career there'll be ups and downs with the career. So it's important to have that life. Speaking of which, when I went back to my PhD the second time around, I canvassed all the PhDs at Caltech and asked them, do you have any tips for success? And my friend Kartik Sheth told me about a three-legged stool. So in grad school, you're roughly spending your time in three ways: coursework, teaching, and research. And at any given time, one of these things at least is not going to be going awesomely. And so to keep that stool from collapsing, you need to bolster it with a personal life. Right? That keeps that stool nice and reinforced. So thank you, Kartik. I have since evolved into a four-legged stool. And yeah, so that I consider to be, I'm a wife, I'm a mother, I'm a writer, I'm a professor. Over all of it is I'm me, I'm just me. And what keeps those things all supported is self-care. And that can mean different things at different times, but it's really crucial. Develop a filter question for requests. Something like, will this help me to fill in the blank? So for those of you who are undergrads, will this help me to get my bachelor's degree? Or will this help me to get into graduate school? Or will this help me to get my PhD? Will this help me to get tenure? Because requests will just increase as you get further and further throughout your career. And if you're in a group, if you're a woman, if you're a minority or a group from a historically marginalized population, you're going to get more requests than anyone else. And so it's incredibly crucial to develop this filter question and to get very comfortable with saying no often. And for those who are not women or not from historically marginalized populations, learning how to say no is important too. Because I trust me, people are saying no, and they're spending time on what matters, what they need to do to get to the next level. And if I keep saying yes to things that aren't going to help me get to the next level, then I'm the one who's missing out. So it's important to learn how to say no. Write every day. Stay open to opportunities. And this is for those of us in academia, of course. Publications, especially in the sciences, is the currency. And I think it couldn't hurt, even if you're not in the sciences or not in academia, writing every day is an incredibly helpful self-reflective exercise. Look for who has what you want, ask them how they got it. So start building your team. People who have done the thing you want to do, ask them how they did it. My mentorship network doesn't even fit on one slide anymore. This is just a snapshot. Anyone who's answered a question from me about a grant, a paper, a fellowship, on the phone, met for coffee, that's a mentor. So start building your network. Again, science, and I argue any academic pursuit or any professional pursuit is a team sport. You don't have to do it alone. And that hopefully will increase the chances of you not looking like this throughout your career, but more like that, maybe like that, and goodness, even like that. Wouldn't it be incredible to spend the bulk of your career looking like that, right? That's my wish for you. I want to thank Bowdoin College, the Kibbe Lecture Fund, my institution and funding sources, and my collaborators for contributing to this work and to the opportunity to be here today with you. And thank you all for your attention.
Thank you so much for your talk. That was truly inspiring in many different ways. And I think we have time for some questions now. Is that, I think a little bit of time in any case. What I suggest is the following. This is a little bit of a complicated setup because we have both people here in person and people online. We'll give people who are here in person the preference. So as long as there are people here, we'll take those questions. Otherwise, we'll also look into the chat box or into the QA box in the webinar and see if there are any questions there. Who would like to be the first one? Don't be shy now.
Thank you for that talk. I'm Madeleine. We've exchanged a lot of emails. And I just wanted you to put a pitch in for tomorrow. You're going to do a workshop with students about the path to thriving. So yeah, tell everyone how much fun it's going to be to go through some of your exercises.
Thank you so much, Madeline, and thank you for all that you did to help me be here. Yeah, so tomorrow I've got 2 events happening tomorrow, and one of them is a colloquium for the undergrad astronomy class that's early in the morning, well, early in the morning my time, not so early your time. It's at 11:40, I think. And then later on in the afternoon, what will be the evening for all of you, I believe 6 p.m. your time, I'll be leading participants in what I'm calling a memoir connected workshop. So I'll be reading from passages from my forthcoming memoir. And then the bulk of the workshop will be self-reflective exercises. I'll be leading participants in their own individual work to help determine where they might want to go career-wise. So we'll be having them do some writing, bring a notebook and some loose-fitting clothes. We'll be doing some mindfulness practice too, and really helping to uncover what is really truly deeply inside wanting to be addressed in that way in terms of a path forward. So I hope you'll join me if you're interested.
Hey there, thanks so much. I have a question that's related to the James Webb Telescope. I understand that it may have the capacity to collect data from atmospheres around some of these extrasolar planets. And I just wondered about the quality of that data and how it might impact your models.
Yes, so we're all really excited about JWST. One of the great things about James Webb is that it carries with it an infrared spectrograph, and that instrument allows us to measure stars' light filtered through a planet's atmosphere. And so if a planet has a given atmosphere, we end up measuring the light, the star's light hits the atmosphere, and that atmosphere will absorb the light according to its specific gas properties. And we can measure the spectrum of the much brighter star versus the planet directly. But when we look at that spectrum of the star, we see chunks taken out of the spectrum, and we can match those chunks to the gases that we know absorb at those wavelengths, and that can tell us what's in the atmosphere of those planets. And we're hoping for some telltale signs that would tell us that only life could put that into the atmosphere, put those gases in the atmosphere. Now, the tricky part is determining what that recipe is. And there are people in astrobiology whose sole job is to determine what we call biosignatures, which are these biological fingerprints of life, what that recipe would be. It couldn't just be carbon dioxide, because we know that there are things other than biology that can make carbon dioxide, namely volcanoes. It couldn't just be oxygen, because we know that carbon dioxide can be split apart by sunlight into carbon and oxygen. We measure the oxygen, we might think that there's life there, but it's really, again, just carbon dioxide. So it's really tricky to come up with a suite of different gases to look for, but we have some ideas. And once we come up with a kind of a suitable recipe based on what we know about the planets that we're looking at with James Webb, we can sort of try to play that matching game and see what we find. So I think it's a very exciting prospect.
that great talk. I was thinking about the elongated orbit challenge in terms of the difference in temperature, and was wondering whether there were any materials that planets might have at their core that had heat capacity that could, with elongated orbits, they could maintain the heat enough when they're in colder parts of the orbit to have that, not whether, I mean, yeah. So I was just wondering whether that might be a possibility.
Yes, and it totally is. I'm glad you brought that up. So just as there is that traditional habitable zone that I showed you the diagram for, people have coined other terms, such as the eccentric habitable zone. That's something that my grad student Igor sort of refined to look at how different stellar types could influence the eccentric habitable zone. And there's a tidal habitable zone. So you could imagine planets due to tidal friction between either the planet and the star, or the planet and other planets that might be in particularly resonant orbits, where that tidal friction is not insignificant. That could be a source of heat. That's really why we know of at least one planetary body within our solar system that hosts an ocean other than the Earth. It's Jupiter's moon Europa. That's primarily due to tidal friction between Europa and other, Io and other moons in the system. And so this tidal habitable zone could be a very strong source of heating. There's also the radiogenic heat of formation. So certain planets might be young enough that they still have a significant source of radiogenic heat. So radioactive decay from some of the different isotopes that make up part of their crust, for example, that could provide heat. So yeah, the having that planet be eccentric, in my mind, does not mean that it could not be habitable. There are a number of different sources of heat that could add additional surface habitability bolstering throughout the orbit.
I've been looking forward to this since I saw the posters. And I was curious, so I am a evolutionary ecology student, and something that I've been trying to find space for is space for speculative fiction and speculative nonfiction in learning evolutionary stories, especially learning stories in deep time. And I feel like a lot of that also applies to how we're imagining what could be in other contexts. And there's been a lot of work that's been done on the speculative fiction work, especially of writers like Octavia Butler, especially on the idea on like how the different worlds that people from outside of these like academic worlds or outside of these scientific worlds imagine what other forms of life could be. I'm curious, people talk about how the arts bring them to the science and bring them to astronomy and imagining these possibilities. But I was curious how you see arts, these creative practices, these imaginative practices that aren't necessarily quote unquote academic, playing a role in how you and others in your field are trying to stretch the limits of like our imaginations about what could be and how it could be.
Thank you. Boy, for a long time I thought, as you saw, that there was the arts over here, science is over here, and there wasn't any crossover. And I have seen that there's so much opportunity for one to inform the other. I mean, my ability to communicate the science is a direct result of my arts and acting background. My imagination, which is sparked from that background and from, I think, my own family history as a child of creative artists, allows me to think about scenarios and look up at the sky and think, what could there be? Also, my exposure to film and TV, that having that imagination that's sparked and allows me to dream. It doesn't mean that someone who didn't have those interests wouldn't be incredibly creative in the science fields too. But I think that so much of who we are can inform what we do. And historically, there's been a lot of like that sort of separation between who we are as personally and who we are professionally. And I like to bring those two together because I think so much of who we are personally informs what we do professionally. And I think, you know, when I was at Caltech, there were some people whose jobs it was to make artist impressions of all of the different Spitzer discoveries. And that was their job. So they were putting together the arts and the accurate, they tried to assign the accuracy that we had from the observational data. And then there is that, but there's a gap there when you get to fill in with your imagination what could be. And I think that's really lovely because that's how we connect with the audience, with the public, is not necessarily worrying about being to the point accurate, but being more focused on building a bridge and inspiring, especially in the younger generation.
Thank you for your presentation. It was very inspiring because I also look like you, and I am happy to see another Black woman in physics. And I have I don't know if it's an insignificant question, but my friends and I have been hypothesizing about this, but in the illustration that you had of Kepler's mission and the planet going around the star, there's a big dip that was caused by the planet going in front of the star. And then there was that little dip when it was on the other side. And I was wondering what that was about.
Yes. Okay. Let me show you. Oops. Okay. I'm not sharing anymore, but I'm going to share again in a second. I'm going to find it. Yeah. I usually talk about this in my courses. Play from current slide. Okay, so here we go. So what you're seeing, I think this will keep going. When you see just the straight horizontal line, you're seeing planet and star. Then planet passes in front of star, blocks out a big chunk of the star's light. So at that point, you're seeing planet, you're seeing star with planet's light, you know, blocking a little bit of it. Then you go back to seeing planet and star. Then the planet passes behind the star and you just see star. So what this is just star, planet and star. I'm gonna do it again. Okay, planet and star, just star, planet and star, planet and star, planet in front of star, planet and star, just star, planet and star. So that little, that's called a secondary transit or secondary eclipse. This is the primary transit because having that planet take a chunk out of that star is the biggest dip. But then when you have the planet's light gone, you have a little bit of dip because you just see the star. And then this is both. Okay. I hope that's clear.
Yeah, I guess my question was also about the exact same thing. I was wondering, how do you determine natural satellites and other celestial objects from exoplanets whenever you're determining their transits?
Yeah, I'm going to give you my theoretical climate modeling answer, not being an observer, but that, remember when I said they check and they check and they check, they can't just take one transit and say, we found a planet. They have to confirm because yes, something could be passing in front of the star beyond besides another planet, they have to make sure it's periodic. And that's going to tell them that that thing is most likely orbiting the star, or more accurately, the planet and the star are orbiting the common center of mass, which happens to be much, much closer to the star because the star is so much more massive. But that something is continuing to orbit. So we need to have more than one transit to confirm. Even then, there could be things like, I think I've heard from my colleagues or observers, things like a binary star system, right, could potentially do a similar thing. So you'd want to, this is why radius information is really important. So remember I said that you can get size information from this transit. So determining the size will also help you to say, okay, if that size, that would be, too small to be another star. This is most likely a planet orbiting the star. So those are some of my initial thoughts as to how they have to, how they can really determine whether it's an actual transit. But yeah, it's they have that. There was something else I was going to say about that transit. Oh, right. So this is why M dwarfs, I said that they're easier to detect. It's easier to detect planets around M stars than hotter, brighter stars, because remember that habitable zone is much closer into the M star. And that means a planet's year is shorter around an M if it's in the habitable zone. It's closer to its star, so it takes less time to go around. And that's really good for confirming transits. You don't have to wait multiple times 365 days. If you're looking for a transit around a G star of a planet in a habitable zone, like our Earth, and you needed more than one transit, you'd have to wait for more than a year, like 2 years at least. But for an M star in the habitable zone, its orbital period is more like 30 to 45 days. So we can confirm a transit in, a couple months, much more reasonable in terms of that. So multiple signals, periodic, multiple transits, and then looking at the size information helps to rule out other things besides planets. Sure.
To the end of this. So thank you so much again for your talk. Thank you for all the great questions. Thanks for joining us tonight. And let's thank our speaker again.
Thank you so much. I had so much fun. Thanks for your attention.